A vector autoregression, or VAR, generalizes an autoregression to a vector of variables. In a VAR of order P, the current vector y equals a constant vector plus E, coefficient matrices multiplying P lagged y vectors, plus an innovation vector. Every equation may include lags of every variable. The innovation vector has mean 0 and a positive definite covariance matrix called omega. Innovations at different dates are uncorrelated under the basic white noise specification, but components at the same date may be correlated. This contemporaneous covariance is important because it means reduced form forecast errors are not automatically distinct economic shocks. Matrix lag notation lets us compress the whole model. We define an autoregressive polynomial in the lag operator. It starts from the identity matrix, subtracts the first coefficient matrix acting at lag 1, and continues subtracting each later coefficient matrix acting at its own lag, all the way out to lag p. Applying that polynomial to y leaves just the constant plus the innovation. This compact form is what makes deriving stability and impulse responses manageable later on. Any VAR of order P can be rewritten as a first-order system by stacking current y with its previous p-1 values. The enlarged transition matrix is called the companion matrix. Its top row contains the original coefficient matrices, and lower blocks simply move each lagged vector down one position. The companion form turns a high-order model into one first-order recursion. Iterating it separates future innovations from the initial state. Stability requires every eigenvalue of the companion matrix to lie strictly inside the unit circle. Then powers of that matrix vanish, shocks dissipate, and long horizon forecasts return toward the unconditional mean. The same condition can be stated with the determinant of the matrix lag polynomial. Lag order is a central modeling choice. Too few lags omit dynamics, leave serial correlation in residuals, and can distort impulse responses. Too many lags introduce many coefficients, inflate estimation variance, and overfit the sample. The preferred order balances dynamic adequacy against the rapid increase in complexity. Information criteria formalize that balance. The AHCAR-EE-CHI criterion applies a relatively light complexity penalty. The Bayesian criterion applies a penalty that grows with the logarithm of sample size. The Hannon-Quinn criterion lies between them. For each criterion, we compare models on the same sample and choose the order with the smallest value. Likelihood ratio tests can compare nested lag orders. The null model restricts all coefficient matrices for the extra lags to 0. Twice the difference between unrestricted and restricted maximized log likelihoods has an approximate chi-squared distribution under regular conditions. The number of restrictions grows with the square of system dimension times the number of omitted lags. Likelihood ratio, score, and Wald tests use different aspects of the same likelihood geometry. The likelihood ratio compares two fitted objective values. The score examines the slope at the restricted estimate. The Wald statistic measures how far the unrestricted estimate lies from the restriction. They are asymptotically equivalent in regular problems, but can differ in finite samples. Residual diagnostics remain essential after order selection. We inspect serial correlation, changing variance, unusual observations, and stability of the fitted routes. A low information criterion cannot rescue a model whose residuals retain systematic dynamics. Nor does a high equation-specific R squared establish a meaningful multivariate specification. Granger causality asks a predictive question. Variable y. Granger causes variable x, if past y, improves forecasts of future x after conditioning on the available history of x and other included variables. The definition compares conditional mean squared forecast errors under a smaller and a richer information set. In a bivariate VAR, y does not Granger cause x when every coefficient on lagged y in the x equation is 0. We test those coefficients jointly with an F-test, a Wald test, or a likelihood ratio test. Rejection means the lags contain incremental predictive information within the specified system. The result depends on the information set, transformations, lag order, and sample period. An omitted common driver can create apparent predictive direction, while noisy measurement can hide it. A failure to reject is not proof that no predictive contribution exists, especially when the model has low power or the relevant effect is nonlinear. Most importantly, Granger causality is not structural causation. Stock prices may predict future dividends because prices incorporate expectations, even though expected dividends help determine prices economically. A linear transformation or a different set of variables can also alter measured predictive direction. Theory and credible identification are needed for a causal claim. Let me leave you with how this fits together in practice. Start by choosing variables and transformations that make economic sense, then settle on a defensible range of lags. Estimate the stable vector autoregression, look hard at the residuals, and only then test restrictions you have stated clearly in advance. And when you report Granger causality, use the phrase to mean incremental predictability, nothing more.